Okay, guys, in this video, we're going to start going into this idea of error and measurement and how, when we measure things, we have to effectively account for the fact that all measurement has error. Okay, so there is no measurement that is done that does not have some sort of error. You can have the best tool, the most precise tool in the universe, and at the end of that measurement, there always is some sort of uncertainty in terms of what that error is in terms of that measurement. Okay. So because of this, scientists have to factor in error in all their measurements, okay? To minimize the effect of error, to minimize the effect of this not perfect world, we do estimations, all right? A lot of students think that estimating is actually creates error. In reality, estimation reduces error because without an estimation, your values would be too high or too low because the estimation brings you closer to the right answer. So here's what we're going to do. We take a look at this couple lines here. We have 0 point and we have a 10 point. And if I bring a bar out this far, I say, okay, how far out is that? So go ahead and take a look at it and make your best estimate in terms of how far that bar reaches out between 0 and 10. Now, doing so, most people will say something along the lines of either 6 or 7, maybe 8 on the way out. Students have told me that they don't choose 5 because they can tell it's more than halfway, which is a good way to do estimating. They definitely don't do 8 or 9 usually because it's not close enough to the 10. So they settle some places it's either 6 or it's 7, okay? Which is a really good estimate in terms of what we have here because we really don't know if it's anything more than 6 or 7. We can't say 6.5 or 6.3 and those kind of deals, okay? And the reason why we can't do that is because when you estimate, you only can estimate a single digit. You can't estimate two things. So in this case here, we know it's not 0. We know it's not 10 because of the lines that are given to us on our measuring tool. So our estimation is between 0 and 10, which happens to be 6. Okay? But we can't say 6 is an estimation and 5. So we can't say 6.5 is our estimation. Now, is there still possible that there are errors here? Absolutely. But with this estimation, it's better than not estimating. Because if we didn't estimate, our choices would say, well, this is either 10 or 0. Well, it's not 0, it's not 10, it's somewhere in between those two numbers. Okay? So from that, we get this rule. When you're measuring, you measure to the precision of your tool. So wherever the lines or the marks are on the tool you're working with, plus you add in your own estimate. Okay? Which means if you think that a length or a volume or a temperature lands exactly on a numerical value, that you estimate at 0.0. Okay? Which means that if you think your measurement lands exactly on a line or exactly on one of our divisions, you would estimate at a 0. So in this case, if you thought it hit exactly 10, it'd be 10 exactly or 10 0 to make that measurement. Okay, but you always want to include that estimate when you're doing your measuring. Now, here's a quick look at all the individual spacings if you want to see that, and you see that it really didn't hit 6 exactly or 7 exactly. It was someplace in between there. Now that we have more lines, we could actually do another estimate and make our measurement even better. So here we can count over, here's our 5 line, here's our 6, here's our 7, okay? So it is somewhere between 6 and 7, so you can now say, well, it's 6.3, or maybe it's 6.4, or 6.2, whatever you think that is, because we now have added a better or more precise measuring system for this, okay? So our estimate now becomes that decimal where it's 6.3, and because we know it's at least 6 and it's not yet 7, okay? So every time you measure, you can measure to the precision of your tool plus that estimate. Now, different measuring tools that we have. We're going to hit the 4 major categories of measuring, and then in lab, you're going to do some of your own measuring to make sure you handle it, okay? So first thing, lengths. Meter sticks, rulers, those kind of things we measure for length. Remember, we do not measure with yardsticks, okay? Those are imperial system type devices. We use a meter stick, which is about a little over 3 inches longer than a normal yardstick. Make sure you align the one end to the 0 point, align your eye with the other end of that to avoid what we call as a parallax, okay? So if we have a line written down here in this picture, and if you look, it goes 8, 8.1, 8.2, 8.3. It lines up exactly with 8.3. So looking straight down at this, we would get 8.3. But if I was looking at this angle or that angle, from some sort of angle, I might read that line as 8.5 or 8.2. Okay, so looking straight down helps us avoid that idea of a parallax. Okay, make sure you're estimating between the lines. All right, so on this measurement, we notice how this line, I believe it hits exactly at 8.3. I think it hits right on that line. So my estimate here is 8.30. Oops. I'm estimating the 0 in this scenario, okay? The tool tells me 8.3. I estimate the 0 in this case. Now, when you're working with volume measurements are very similar to length measurements, but because we're using a liquid inside a graduated cylinder, we have a couple little things that happen to us. So first thing, make sure you use a graduated cylinder when you do volume measurements, not beakers. Beakers aren't really designed for precise measuring. They can get you close, but not very precise. So we use graduated cylinders instead. Make sure you also use the right size graduated cylinder. So you want to use a graduated cylinder that matches the volume you're measuring, okay? So you wouldn't want to use a 500 milliliter graduated cylinder if you only needed to get 5 milliliters, all right? In your drawers, you have a 10, a 25, and a 100 milliliter graduated cylinder. So use the one that matches whatever volume you're trying to do, okay? We always want to measure to the bottom of the meniscus. Now, when you have water or any other liquid actually inside a graduated cylinder, because of the heat adhesive forces on the outside of the glass of the water, it actually pulls the water up a little bit because of an attraction there. Because of that, we get a curved line with our water or our fluids. When that happens, we need to know where to measure. Well, you don't want to measure to the top of the curve because you're actually missing some of that volume. You always want to measure to the bottom of that curve, what we call the bottom of the meniscus. So this curve is like the meniscus. It's really not unlike the meniscus in your knee. It's actually a curve-shaped part of your knee. Same idea, it's a curve to it. Make sure you line up eye level again, look straight across, and you hit that meniscus. Now, as before, make sure you're estimating between those lines. So if we take a look, here's 30, here's 35, this is 36, this is 37, so our meniscus falls someplace between 36 and 37. The tool gives me that. So my measurement here would be 36.5. I think that hits exactly halfway between those two things. If you think it's a little bit lower than that, maybe you call it 36.4, and that's okay also, because the last digit is always an estimate. Now, when we're working with volume, sometimes we need to get very precise measurements. And because that meniscus might be dealing with a clear fluid, or something we can't see very well, it's sometimes hard to see right where that meniscus is. A little trick to help is you take a piece of paper, again, this is actually a graduated cylinder that's from our lab itself, put a thick black line behind it on a piece of paper and move it up ever so slightly right by where you think the meniscus is. When you do that, at some point, if you're looking straight on, you're going to see a reflection of that black line off the meniscus, and we can kind of see it right here. That black line, and that black line then gives you a reference point to make your measurement, okay? So if you look, this is 80, so we have 81, 82, 83, 84, this is 85 right here, it's a little bit longer line. So then we have 86, and I might think this is exactly 86 milliliters, but because of that black reflection, I see that the black line actually dips below the white line very closely if you're looking tight, really close on this. So my estimate here would probably be 85.9 milliliters, not 86.0, because I see that black line drop below the white line, which means that the meniscus is slightly below that, so I'm going to go 85.9 milliliters. It gives me a little bit better estimation and a little bit more precise measurement to do, okay? So that's kind of a tip or a trick you can use when measuring volume. Now, when you're measuring mass, we use electronic balances. So there's no balances back and forth. We have to put masses on and slide little things around and make measurements. It's more about using the balance properly, okay? So first step is make sure you zero out the balance. Our three types of balances have different zero buttons. We have a little zero button here, we have an on zero button here, and then over here this one says TARE, T-A-R-E, which is a fancy word for zeroing it out, okay? Once you get ready to use a balance, always use some sort of barrier. So use a measuring cup, use a little beaker, use a piece of paper, something where you're not putting chemical directly on the pans of our balances. Okay, so we don't ever want to make that contact between chemical and the pans because these are just metal and they could chemically react. Take a reading when the icon appears. Okay, we have very precise balances in our room. They measure out to 1/100th of a gram, or basically a centigram, which means that if a person walks by as you're measuring something, it actually can vary the mass depth by just the air pressure and the air currents that go by it, okay? So because of that, you're always going to see the numbers moving and jumping slightly. They're never going to sit still perfectly for you in most of our balances. What they have built in for us is an icon. So this balance, you can see right here, it looks like a little bit, it actually looks like a little balance. This balance, the glare is a little bit hard, but there's actually a little star right there that pops up. This balance is being cut off by the depth of the screen, but there's a little, like a little zero or a little circle up in this right-hand corner that happens. As soon as you see that icon in any of these three balances, whatever number reads on that screen is the number you take, because it's telling you, hey, I'm done, here's your answer. Do not add an estimate here, because for a balance that does electronically, it's doing the estimating for you as part of its circuits, trying to make sure to get that last digit as precise as it possibly can for you. And then last but not least, use the same balance for the whole experiment. When you're working with balances, because there are slight differences between them, and they may not all be calibrated perfectly the same, by using the same balance, you're minimizing error the whole time through. Now, when it comes to safety in these balances, one thing to be aware of, depending on the version of the balance you use, some of our balances can only hold 150 grams, which we now know is less than a third of a pound. So it's not very much mass. So please make sure when you use the balances to not put anything heavy on them to try to take a mass of those. They really aren't designed for that. And these things cost $300+ each. So if we ruin one by messing around, by putting something too heavy on it, that's a $300 fine that you're going to have to take care of to help me replace a balance that shouldn't have broke because of your actions. So please make sure that we only put things on the balances that we have designed from our labs to do so. All right. Now, the last measuring thing is temperature. When we measure temperature, we have two different measuring tools that we use. We have a digital thermometer and we have an analog one. The digital one works very much like the balance, where you just put it in your solution and you read the number that comes off. A couple things to make sure is make sure it's in Celsius, because they do have a switch in the back that allows you to switch to Fahrenheit. And then second thing, for both thermometers, when you're taking a temperature, you always want to have the thermometer floating or suspended in the middle of that solution. You don't want them touching the glass on the outside or resting on the bottom, because it will take the temperature off the bottom or off the side. You kind of want to put it in the middle as you're taking temperatures with that kind of stuff. Okay. Again, with the digital display, don't add an estimate. With the analog one, here you do put an estimate in between those lines. Okay. And if you take a look, both of these are running and they're both giving us a temperature. And the alcohol thermometer, if we go up to 0, 10, 20, if you look really close, it's kind of hard to see from this picture, but the line definitely goes above the 20 by a little bit. And if we could roll over here and see those little markings, it hit really close to about 21 degrees Celsius. So our estimate would be 21.0, or maybe 21.1, or maybe 20.9 degrees Celsius. Well, our digital display is giving us 20.9 as its best reading. So in terms of accuracy, excuse me, in terms of accuracy or precision, the electronic one isn't really better than the analog. It's just easier for us to read. Okay, so we use both in lab. Primarily, we use the digital one just for ease of use, but both are valid and both provide the same amount of accuracy as we do our stuff. All right, guys, that is the stuff on measuring. We'll end the video here. Thank you.